of small f of x. Okay, let's give an example. So we have example 5.1.1. We want to expand as Fourier integral the function f of x, which is equals to x in the interval between 0 and 1 and in 0 elsewhere. So I make life easy for you. In 0 elsewhere, you're only integrating between 0 and 1. So life is very easy here. So what do we do? So what we want to do is that we want to find this f of x. So we're using 5.1. So basically, you only need to find capital F of k. You use this to compute the capital F of 0 and 1 and 0 elsewhere. So we must first compute our capital F of k. This is the formula for computing a capital F of k. Capital F of k is just 1 over 2 pi minus infinity to infinity f of x, where f of x is power minus IKS dx. Then you discover that f of x is 8 between 0 and 1 and is 0 elsewhere. So basically, you are integrating between 0 and 1 because the integral of 0 is 0. So s1 is 0. So we are integrating between 0 and 1. 1 over 2 pi integral from 0 to 1. 8 because f of x in that interval is 8 into the power minus IKS. So everybody can integrate this. So when you integrate this, this is what you're going to get after the integration. So we are going to get our capital f of k will be minus 4i over pi k into 1 minus 3 to the power minus IKS. Look at what I've done here. So I've made use of the fact because say you got 1 over I. So what is this 1 over I? So 1 over I is the same thing as minus I. So that is why you got minus I here. So 1 over I, what you do is to rationalize the denominator. So you got this as minus I. So this 1 over I is the same thing as minus I that you got here. So once you get your capital F of k, which is minus 4i over pi k, 1 minus 2 to the power minus ik. So substitute back here. So just plug it in here. You plug it here. So this is capital F of k. So this is basically your Fourier transform of small f of x. And the Fourier transform will be equals to x in between 0 and 1. It's going to be 4 between s equals to 0 and s equals to 1. Because those are the end points between 0 and 1. So you take the average of 2, as I've taught you in your under your Fourier series. Now you discover that f of s is not defined as s equals to 0 and s equals to 1. At s equals to 0, limit from the left is 8, and limit from the right is of 1 is 4. So the two are not the same. So f of s is not defined for s equals to 0 and for s equals to 1. So thus the convergence of the Fourier integral at f of s of integral to f of x will just be 8, which is the average of 8 and 0. This is 8 plus 0 over 2, which is 4. So this is as a consequence of the fact that f of s has a jump discontinuity at s equals to 0 and s equals to 1. So s equals to 0 and s equals to 1 are called the jump discontinuity of f of x. So at that point, f of the Fourier integral does not actually converge to f of x. Okay. Now let's take another example. We want to expand as Fourier integral this function. F of x is x in between 0 and 5 and in 0 elsewhere. So I always have my f of x defined this way to make life easy for you, so that your integration will be very easy for you to integrate. So what we are going to compute is to compute to f of k. So we must first compute a capital F of k. Once you get to f of k, you just plug it back. You substitute back to small f of x. It's a definition of small f of x. So this is our capital F of k, 1 over 2 pi, target from minus infinity to infinity, f of x is to the power minus IKS. But life is easy because f of x is x between 0 and 5 and is 0 elsewhere. And when you integrate 0, you get 0. So that means integrating from minus infinity to infinity is the same thing as you integrating from 0 to 5 of f of x. So f of x is x. Between 0 and 5, f of x is x. So you substitute your f of x to be x, so you integrate this. Then you must use your integration by part to do this. So I've taught you over time how to use integration by part. You also learn this in your MATH354. So for you to integrate this, you must use your integration by part. So if you use integration by part, this is what you will get. Then you put your limit of integration, which is 0 and 5. So this is what you get as your capital F of k after integrating by part, and you are putting and after putting your limit of integration. So you also make use of the fact that minus 1 over I is the same thing as I. Minus 1 over I, because you get minus 1 over I occurring in the denominator here, it's just the same thing as I. Okay. So what we do then, this is the formula for computing the Fourier integral of f of x. So we computed capital F of k, which is this. So we just substitute back. So this is our capital F of k, and this is e to the power of IKS dk. So this is the Fourier integral of the function f of x. It goes to 0 if x is negative. It goes to x is if x is in between here, and it goes to 5/2 as x equals to 5. And it goes to 0 if x is greater than 5. At x equals to 5, it has what we call the point of jump discontinuity. So you take the average of 5 plus 0/2. So which is 5/2. So I want to define what I call the Fourier transform. So the first thing that I've done is I've defined the Fourier integral of a small f of x. There's a connection between Fourier integral and Fourier transform. Is that okay? If you want to compute the Fourier integral of a small f of x, you must first compute the Fourier transform, which is capital F of k. So capital F of k is related to small f of x. So the next definition gives you the derivation for the Fourier transform of small f of x. So whenever you want to compute the Fourier transform of f of x, small f of x, you are going to use 5.2. So 5.2, which is f of k, gives the Fourier transform of f of x. Now, note what the Fourier transform is, which is 5.2. Now, for the Fourier transform, I can also get what I call the Parseval identity that I got in our Fourier series. Okay. Now, if you are given two functions, f and g, that are defined over this interval, infinite interval, and you assume that both of them have Fourier transform. This is for f. You also have the one for g. So the inner product of f and g is defined as 5.3. Is that okay? So it is possible for you to then have 1/2 pi inner product of f and g to be equals to the Fourier transform of f, the inner product of the Fourier transform of f, and the Fourier transform of g. So 1/2 pi, the inner product of f and g. This is inner product of f and g defined this way. It's just the same thing as the inner product of the Fourier transform of f, which is capital F, and the Fourier transform of small letter g, which is capital G. So in your 5.4, if you replace your g with f, so this becomes inner product of f and f, and this becomes the inner product of Fourier transform of f, Fourier transform of f. So we are going to get 5.5. We are going to get 5.5. 5.5 is what I call the Parseval identity for Fourier integral. So 5.5 is very important. It's what I call the Parseval's identity or Parseval identity or Parseval equation for the Fourier integral. So I can give you a function and ask you to find the Fourier transform, then I can ask you to verify the Parseval identity. So if you want to verify the Parseval equation identity, you must that the left hand side is equal to the right hand side. So you compute the left hand side, you also compute the right hand side. You must show that the two of them are equal to one another. Okay, so let's look at this example. So we have our function f of s, which is 3 if x is in between 0 and 1, and the 0 elsewhere. So this type of integration is very easy for you to integrate. So basically, I'm only integrating between 0 and 1, which is f of s is 3. So we want to find the Fourier transform of this function and also verify the Parseval equation, which is 5.5. So we want to see show that equation 5.5 holds for this function. Okay, so what do we do? Now, look at my 5.4. I told you 5.4, 5.3 that 5.2, that the Fourier transform of small f of x is given by 5.2. If we want to find the Fourier transform of f of x, this is given by this 5.2. So to find the Fourier transform of f of x, we go to use our 5.2. So using 5.2, the Fourier transform of f of x is given by this. This is the Fourier transform. Okay. So life is very easy because instead of integrating between minus infinity to infinity, we know that f of x is only defined as 3 between 0 and 1 and is 0 elsewhere. So basically, you can integrate between 0 and 1 to make your life easy. So f of x is 3 between 0 and 1, and this is e to the power minus IKS. F of x is equal to 3 in that interval 0 and 1. So you can integrate this, which is very easy to integrate. So when you integrate this is what you're going to get after the integration. So this is what you're going to get after the integration. So this is the Fourier transform of f of x in that interval. So I put some other use information there for you that you can write your sin k of x as this. If your sin k of x is equals to this, then you can put your k of x as k over 2, then you are going to get this. So look at this. Instead of you can replace this guy here with 2 sin k over 2. And I told you the other time that what 1 over I is. So okay, you already got 2 over I there. So the whole of this is just 2 sin k over 2. So this is what this one will give you. So that means e to the power I k over 2 minus e to the power minus I k over 2 over I is just the same thing as 2 sin k over 2. And this is the k here. So this is this part here. So this is the Fourier transform of that f of x. So the first transform of f of x is given is this. So the next thing is to verify our Parseval identity or Parseval equation. So this is the Parseval equation. So what we're going to do is that we're going to show that the left-hand side equals to the right-hand side. So you compute your left-hand side and you also compute the right-hand side. Show that the two of them are the same. Okay, let's compute the left-hand side. So the left-hand side is just 1 over 2 pi, taken from minus infinity to infinity, and so to f of x raised to the power 2 dx. Because I've told you f of x is equal to 0 outside the interval 0 and 1. So you are only integrating between 0 and 1. Between 0 and 1, f of x is 3. Is that okay? Now, because the f of x is positive, the modulus is positive, just the same thing as f of x. So to the power 2, you get 9. So you're integrating 1 over 2 pi, taken from 0 to pi, integrating 9. So this will give you 9 over 2 pi. So the left-hand side, this guy here is 9 over 2 pi. Now let's look at the right-hand side. This is the left-hand side, 9 over 2 pi. Let's look at the right-hand side. So the right-hand side is integral from 0 to infinity, absolute value of capital F of k, or raised to the power 2 dk. So we computed our f of k earlier, which is the Fourier transform of f of x. So this is our f of k. This is our f of k, which is the Fourier transform of f of x. So let's put f of k, let's substitute back into the equation. So if you come here, this is my f of k, this is my f of k. You put the absolute value. You put the absolute value and you multiply out. So this is going to give you 9 over 4 because you have to raise to the power of 2. You have to raise to the power. So when you raise to the power of 2, 2 to the power of 2, so you got this one 4 pi square. You get k to the power of 2, you get k square. 2 to the power of 2, you get 4 square. Sin k over 2 to the power of 2, you get 4 sine square k over 2. But when you expand this guy to the power of 2, you must check it's going to give you 9. So you get the expansion as 9. So you are integrating with respect to k, because the formula says the k with respect to k. So 9 over 4 pi is a constant, take it out. Then you are integrating this. Okay, so but you are integrating with respect to k, unlike the one with respect to x. This is with respect to k. So you must try to change your variable a bit. So I try to change my variable. So if I put my theta as k over 2, the theta over the k will be equal to 2 the theta. K is 2 theta, k square is 4 pi square. So if I substitute everything here, so I will get taken from minus infinity to infinity, sine square theta over theta square d theta. This is a standard integral. This is standard. This integral is standard. This is a standard integral. So whenever you're integrating this, it's just the same thing as pi. Is that okay? You can see page 70 in the type lecture note. So look at page 70 in the type lecture note. So if you look at page 70 in the type lecture note, you're going to get this. So that means the whole of this one is pi, which is this pi, and you multiply by this. So we are going to get pi, we cancel pi, we have 9 over 2 pi. So look at the left-hand side. The left-hand side is 9 over 2 pi. The right-hand side is also 9 over 2 pi. That means the Parseval equation or Parseval identity is satisfied. So that means we have verified the Parseval equation or the identity. Okay, so let's look at the next example, which is 5.2.3. So we are given the function f of x, which is 1, if absolute value of x is less than 1 over 6. and is 0 elsewhere. So we want to verify the Parseval identity. So we are given f of x. Okay, we want to find the Fourier transform first. That means which is our f of k. And this is f of x is defined as 1 if modulus of s is less than 1 over 6 and is 0 elsewhere. Okay, so modulus of x. So you must first of all find out your intervals of integration. Modulus of s is less than 1 over 6 implies minus 1 over 6 less than s less than 1 over 6. So that means f of s is equals to 1 if minus 1 over 6 is less than s less than 1 over 6 and it is 0 elsewhere. So absolute value of x less than 1 over 6 is the same thing as minus 1 over 6 less than x less than 1 over 6. So you are integrating f of x between the interval minus 1 over 6 and 1 over 6, and the value is 1 and it's 0 elsewhere. Okay, so our life is very easy because outside the interval minus 1 over 6, 1 over 6, f of x is 0. So if you integrate it, this is the Fourier transform of this small f of x. So f of k by definition is the Fourier transform of small f of x. We are to integrate over minus infinity and infinity, which is an improper integral. But f of x is 0 outside minus 1 over 6, 1 over 6. So invariably, we are only integrating between minus 1 over 6 and 1 over 6. And f of x at that point, at that interval, is 1. So this is f of x at the interval, minus 1 over 6, 1 over 6. Outside the interval, f of x is 0. So everything is 0. So don't bother integrating, because if you integrate 0, you are going to get 0. So when you integrate, this is very straightforward. So when you integrate this is what you're going to get. Now, to make life easy for you when you are using Parseval identity, so you must know that sine k over 6 is the same thing as e raised to power I k over 6 minus 6 to the power minus I k over 6 over 2i. So this guy here, replace it with 2 sine k over 6. So the whole of this one is just 2 sine k over 6. So this is what you're going to get. Okay, so that is our Fourier transform of that function f of x. So we want to let's verify the Parseval identity. Parseval identity is this next line. So this is the left-hand side equal to the right-hand side. So let's start with the left-hand side. The left-hand side is always easy to compute. So this is the left-hand side. F of x is 1 only in the interval between minus 1 and 6. So outside the interval, f of x is 0. So f of x is equals to 1 in this interval and is 0 elsewhere. So you have 1. When you integrate this, you get 1 over 6. So that means f of the left-hand side of the Parseval equation is 1 over 6 pi. 1 over 6 pi. Okay, let's try the right-hand side. The right-hand side is giving us integral from minus infinity to infinity. Absolute value of capital F of k. Capital F of k is the Fourier transform of small f of k, f of x. So raised to the power 2dk. Then you must go up a bit where we computed the Fourier. This is the Fourier transform of small f of x. So this is your capital F of k. This is your capital F of k, which is the Fourier transform of small f of x. So you substitute back in there. So you substitute your f of k with this guy. So you substitute it here, then you square. If we square it, you have so 2 we cancel 2 is already gone. Pi square k square as the denominator. So pi square is a constant. You are integrating with respect to k, and because of that, k is not a constant, so you cannot take it outside the integration. It's only pi that is a constant, so you can always take pi outside the integration. So you are going to integrate this. So I try to change the variable. So this is not straightforward to integrate. So to do that, I change my variable a bit. So put a theta as k over 6. The k becomes 6, the theta. K square becomes 36, the theta square. I told you the last time that this is a standard integral. Whenever you're integrating minus infinity to infinity, sine square theta over theta square, the theta, you always get pi. So you don't need to verify this. It's a standard result that you can always quote. So the whole of this here is just pi, which is pi. So pi we cancel pi, so we have 1 over 6 pi. So the right hand side of the Parseval identity is 1 over 6 pi. Let's look at the left hand side. The left-hand side is 1 over 6 pi. So 1 over 6 pi. So that means the left-hand side is equal to the right-hand side. So that means the equation f of x, we should define this way. That means the equation f of x, we should define this way, satisfy the Parseval's identity or Parseval equation. Okay. So what I want to do now is what I call the complex conjugate and the Jordan's lemma. I want you to pay attention to this. This is basically what we have done. We need just some little explanation and manipulations here. So we want to find the complex conjugate and the Jordan's lemma. Now, we know that we often need the residue theory. Anytime you want to evaluate the integral of this form, you can always use some residue theory, which I taught you last week. If I want to integrate integral of this form, I want to integrate, this is my a function and over a particular circle. So, using the residue theory, integrating this is just 2 pi I, the sum of the residue at the singular point of this function, the integrand. So you find the residue are those points that are above the upper half plane, that are in the upper half plane, So you compute the residues, you sum them together, you multiply the sum by 2 point I. So by residue theory, this is the integral of our functions, the value of the integral of this form. So as I've said, you're taking the sum over all the singular points of f of z that are above the upper half, the upper y-axis. Okay. So at this point, the Jordan's lemma, you can look at page 39 in that typed note. Look at page 39 of the typed note. I make a reference to it. So at this point, the Jordan lemma is usually invoked, which in practice allow one to disregard the integral over the semicircle. So you can take away the integral over the semicircle. So here, yes. Hello? Hello? Is someone talking? Okay, so let me round up. I'll give you some time to ask to make a comment on that question at the end of the day. So now here we are going to deal with integral of this form. So we're going to deal with the integral. We want to find the integral f of x e to the power of minus ikx, where k may be positive, negative, or 0. So we want to take k for the whole of the real line. So we want to integrate integral of this form for the whole of the real line, for the whole of R. In that case, our case may be positive, may be negative, or 0. So if k is positive, we are fine. We don't have problem with negative k. We don't have problem with negative k. For negative k, if k is negative, for negative k, we have minus k to be positive. So in that case, we can use our residue theory. So we can always make use of this. So this makes life easy for us. But we may have a problem in which our k is positive. So for k is negative, we don't have problem. Now, for positive case, if k is positive, then minus k is negative. And so Jordan lemma is not applicable. But I will tell you what we'll do at that case. So if you suppose that f of f is 3, then if you use the derivation of f of k, then put your k as minus k. If you put your k here in the derivation of f of k is the Fourier transform of f of x. So if you put your k as minus k, you're going to get this. Is that okay? So let us call this the conjugate of this. So when you put your k, this is a case in which you have f of k as the Fourier transform of f of x. So if you put your k as being negative of k, so put k here as negative of k. So now call this capital F of k bar. So we call this the conjugate of this one that is here. Yeah. So what do we do? Thus, for the f, we always have our f of k as the complex conjugate of my f of minus k. Note this. Please don't forget 5.6. I will continue to use 5.6 over a period of time. So don't forget 5.6. We are going to use it to solve some problem. Now, whenever a function is a real function, f of x is real function, always take your f of k as the complex conjugate of f of minus k. So this bar means the conjugate because this is going to give you a complex number. So just take the conjugate of the complex number. So 5.6 can be used for f of k without calculation. You can just use 5.6 for f of k without using computing anything. So once you get f of minus k, you can always find f of k. Once you get f of minus k, you can always find your f of k. Okay, so let us see. Let me do an example for you. So I want to find the Fourier transform of f of x given this way. So you must know that you are integrating over the whole of R. So I want to find the Fourier transform of f of x, small f of x, which is c over s squared plus c squared, where I assume that my c is a positive number. So the Fourier transform is given by definition. This is the definition of Fourier transform. Is that okay? This is the definition of Fourier transform. This is the definition. So what we have done is that what we're going to do, let's just put to f of x. F of x is this guy here. F of x is c all over s squared plus c squared. So put f of x here. So this is what you get. This is your f of x. So just replace f of x with c into s squared plus c squared dx. So now for k negative, we don't have problem if k is negative. If k is negative, we use the residue theory with Jordan's lemma. So since minus k is positive, if k is negative, minus k is positive, then we are done. So if k is negative, minus k will be positive. And because of that, we can use the Jordan's lemma with the residue theory. Okay, so this is look at the integrand. This is the integrand. Everybody look up. This is the integrand. The integrand is c e to the power minus IKS over s squared plus c squared. So this is the integrand. So I take it as f of z. It's a complex function, f of z. So I'm going to use the residue theory to compute this. I'll use the residue theory. So let me look at the singular point of f of x. The singular point of f of z are where the denominator is equal to 0. That is where c squared plus z squared is 0. So I'm going to get my z is plus or minus ic. Plus or minus ic. But we want to integrate over a contour, which is a semicircle. And this is the upper half plane. So z equals to minus ic is not in the upper half plane. It's in the lower half plane. But z equals to ic, c is a constant greater than 0. So that is why we assume here that our c, so if our c is assumed to be greater than 0, our c is positive. So since our c is positive, z equals to ic will be the one that will be at the upper half plane. If our c is negative, z equals to minus will be the one that is up. So that is why we have to make an assumption that our c is positive. So that means only z equals to ic lies in the upper half plane. So if you draw your x and y as 6, so you are talking about this side. This is the upper half plane, not down, below, not below the x-axis. Okay. So how do we find the value of this integral then? I told you how to compute this integral last week using residue theory. So now it's I2 pi. You go to get the residue of f of z at the singular point that is at the upper half plane. The only singular point that is at the upper half plane is z is equals to ic. So compute this residue, which is this is so. But if I don't get the full recording, that means I have to upload the one for group 2 tomorrow. So I have the network be fine tomorrow. So okay. Now what I'm saying is that there are two singular points for f of z. The singular point the singular point is where c squared plus z squared equals to 0. So which is going to be z equals to plus or minus ic. So, but we only take the singular point that is at the upper half plane. Since we assume that our c is greater than 0, that means z is equal to ic will be the only singular point that is at the upper half plane. So if we want to evaluate this integral is just 1 over 2 pi times this is your f of x times the residue of f of z at the singular point that is at the upper half plane. If two of them are at the upper half plane, you have to compute the residue at those 2 points and add. But only z equals to ic is at the upper half plane. So you compute at z equals to ic. So what to do is just integrate this, differentiate to z squared, which is 2z, then put on z equals to IC. You put on z equals to IC here. So anywhere you see z here, replace this z with IC, replace this z with IC. Then this is what we're going to get. So make use of the fact that I square is equal to minus 1. I square is minus 1. So this I square here is minus 1. So minus minus is plus. So we get e to the power kc over 2. So this is your f of k for k negative. We always use Jordan's lemma and residue theory for the case in which your k is negative. Because if your k is negative, minus k is positive. That is the idea. Don't forget this. This is a tip for you. When your k is negative, minus k is positive. Then you can use your Jordan's lemma with residue theory. So this is a case in which our k is positive. What we want to do for all k, for k positive, k negative, and k zero. Okay? So for k that is positive, then you are going to make use of your 5.6. You just get the conjugate of this. This is for the case in which k is negative. For the case in which k is positive, you just take the conjugate of this using 5.6. Look at what I told you in 5.6. Go up again to 5.6. You don't need to stress yourself. Very straightforward. This is for the case in which your k is positive. For the case in which k is positive, you take the conjugate of minus k. You take the conjugate of that. So we already got our f of k. This is our f of k for k that is negative. So f of k by definition will be equals to, so if you replace your k with minus k, so that is the conjugate of f of minus k. Are you following? That is, this one is conjugate of f of minus k. So what is the conjugate of e to the power minus kc? Which is going to be the conjugate of this f of k. The conjugate of this is just e to, so f of your f of minus k, meaning that you replace your k with minus k. So you want to put a compute f of minus k. So this is f of k. You replace your k with minus k, so it becomes e to the power minus kc over 2. So this is f of minus k. Then find the conjugate. When you find the conjugate, because this is a real number, you must know the conjugate of a real number is the same as a real number. So I put a note here. Whenever z is a real number, z equals to z conjugate. Whenever z, that is how to know a real number. For any real number, the conjugate is equal to itself. Okay, so because e to the power minus kc over 2 is a real number, then it will be equal to its conjugate. Okay, then, so thus we have, this is our f of k when our k is less than 0, which is negative. And this is f of k whenever our k, this is for the other one, whenever our k is positive, this is our f of k. Whenever k is positive, this is our f of k. Whenever k is negative, this is our f of k. But we can combine the two together. Oh, sorry. We can combine the two together. Oh, sorry. We can combine the two together. Okay, let me go up a bit. Okay, so this is our f of k where k is negative. This is the part we computed using our Jordan's lemma and residue theory. The case in which k is positive is the one we use this formula here, but we can combine the two. If you combine the two, it's going to give you 1 over 2 e to the power of absolute value of k, c. So when you combine these two, you can get this. This is the combination of the two. So this is your f of k is the Fourier transform of f of x for all k's. K negative, k positive, k zero. Okay, let's do another example. Okay, we want to find the Fourier transform of f of x, which is this guy here. 1 over x minus 4x plus 5. So the Fourier transform by definition is this guy. This is the definition of Fourier transform. Is that okay? So we only computing f of k for all k's. We computing capital F of k for all k. K 0, k positive, k negative. Which is 1 over 2 pi. Target from minus infinity to infinity. E raised to power minus I k x f of x ds. So just replace your f of x here. Plug it here. Okay, so we get this. So we want to compute this for all k's. Now, there are two things we must do. The first one, for the case in which our k is negative. If our k is negative, minus k is positive, then we can use Jordan's lemma with residue theory. So this is the integrand. The integrand is our f of k, f of z, f of z. Okay, so you must get the singular point. The singular point or the poles are where z squared minus 4z plus 5 is equal to 0. Compute this, equate it to 0. So you're going to get z1, 2 plus I, z2, 2 minus I. But you want the singular point that is at the upper half plane. 2 minus I. If you draw 2 minus I, this is your x and y axis. So 2 along the y axis minus 2 minus I will be somewhere here below the upper half plane. 2 plus I, 2, 1 will be at the upper half plane. So will be at the upper half plane. So only 2 plus I is at the upper half plane. So because of that, I'm going to discard the other singular point, which is 2 minus I, because it is below the upper half plane. Okay, so now for k that is negative, minus k is positive, using residue theory and Jordan's lemma, so f of k, the Fourier transform will be 1 over 2 pi. This is this guy here. So now 1 over 2 pi, using residue theory now, 1 over 2 pi. Please put your circle here because we're doing residue theory. Okay, it's fine, yeah. So 1 over 2 pi, this is 1 over 2 pi that is outside here. The integral of this one is 1 over 2 pi. Compute the residue of e to the power minus I k z over z squared minus 4z plus 5 at the singular point z equals to 2 plus I. Okay, so once you do that, this is what you just differentiate the denominator. So you get 2z over 4. Then put your z throughout as 2 plus I. So you multiply dz with 2 plus I. You multiply dz with 2 plus I. So when you do the computation, you are going to get this guy here. So use the fact that I square is minus 1. I square is minus 1. Okay, so this is your f of k. This is your f of k for k less than 0. Remember, we want to compute for all k positive, k negative. Okay, for k greater or equal to 0, we must make use of this identity. For k greater than equal to 0, f of k will be equal to the conjugate of f of minus k. This is your f of k. In f of k, what is f of minus k? F of minus k means that you replace your k here with minus k, you get minus k. Replace your k with minus k, we get plus 2k. So this is f of minus k. Then get the conjugate. Now this guy here is a complex number. You know how to get the conjugate. So the imaginary part, you change the sign. If it is plus, it turns to minus. If it is minus, it turns to plus. Since it is minus plus here, you turn to minus here. So this is the conjugate of this. So this is f of k for k greater than 0. Okay, look at the two. This is f of k for k less than 0. This is the one we computed using Jordan's lemma and residue theory. Now, how do we get the one for k greater than 0? We put our k to be minus k here and take the conjugate. So this is what we get. Okay, when you combine the two together, so that means f of z for all k, negative, positive. For k that is negative, this is our f of k. For k that is positive, this is our f of k. Then you must know how to combine the two together. Now, you see, this depends on k. So if you want to combine the two together, you see 2ik is here, 2ik here is here. So this is e to the power k to the power minus k. So you can play around this because this guy here is 2ik, 2ik. So it's the same. Nothing, you can do nothing to this. This is k, this is minus k. If you want to combine these two together, you can take it as modulus of k, because modulus of k is minus k. If k is negative, minus become plus. Modulus of k is k is minus k if k is greater than k is greater than 0. So with that, when you combine these two together, you are going to have this. So this is true for all k. So this side is true for k that is negative. This is true for k that is positive. But when you combine the two together to form one, you can have this. So this is true for all k. So this is true for all k. Okay, let me give you the last example. We want to do the same thing the last time. So let me give you the third example. We also want to find the Fourier transform of this function here. So this is my Fourier transform. I'm doing the same thing over a period of time so that you can get the tricks of doing this. So this is my the Fourier transform of f of k is given this way, f of x. So it's a function of k. So put your f of x, plug it in, so you get this. Okay. Now, take the case in which your k is negative, because you must get this for all k. K, negative, positive, and 0. Then get the singular point of this function. The singular point is where the denominator is equal to 0. So where x squared. You can turn your x to z, is the same. Z squared into z squared plus 1 is 0. So get z equals to 0, z equals to plus or minus I. So you want that is in the upper half plane, z equals to minus I will be below. Z equals to 0 and z equals to 1, I will be above the upper half plane. So we're going to compute the residue at z equals to 0 and at z equals to I, not at z equals to minus I. Okay, so for k that is negative, minus k is positive. So evaluate this integral at two residue at the two singular points. The first one, z is I. The second one, z is equals to 0. So 1 over 2 pi. This is 1 over 2 pi. 2 pi I. Compute the residue at z equals to I. Compute the residue at z equals to 0, and multiply by 2 pi I. So once you do that, so this is what you're going to get. Eventually, this is what you are going to get at the end of the day. So you go to get I into 1 minus I into 1 minus e to the power k over 2. This is for f of k. You need f of k for all k. K positive, k negative, k 0. So for k less than 0, this is f of k. So for k greater or equals to 0, what must you do? So always use 5.6. Don't forget 5.6. The step is just straightforward. So once you compute for k negative, for k positive or greater or equals to 0, you just make use of this this relationship, 5.6. So what is f of minus k? F of minus k means anywhere you see k here, replace with minus k. You know we got k here, so we replace our k with minus k. So we have 1, we have I, we have 1, we have 1 minus. Replace your k with minus k, then get the conjugate. So you have to get the conjugate. The conjugate means that the imaginary part. The imaginary part that is having I, the sign change. So I becomes minus I. So this is f of k for k that is greater than 0. So try to combine the two together. This is for k less than 0. This is for k greater than 0. So look at the ones that depends on k. The side that depends on k is this side here. Is this side here, is this side here. So which is the same as modulus of z, the modulus of k all over k. And so this is the combination of everything. If we are combining two together for all k, this is what we are going to get. Look at the fact that I've made use of. Modulus of k over k is just minus 1 if k is greater than 0, and 1 if k is less than 0. So this is going to be the combination of the OT. Okay, so that is the end of the lecture for this week. I'm going to put the tutorial for this week online. So I'll be generous to you because I know your situation back at home. It's not easy to study back at home and the facilities are not there. So what I'm doing is to try as much as possible to provide the solutions and put online for you, so that you have to work on your own between maybe Monday to Friday, then cross-check your solutions with mine over the weekend. And the way we're going, around the middle of July or towards the 3rd week, we're going to round up the lecture. So what I will do, if there's still time, I'm going to spend the remaining time to go over the tutorial with you. Is that okay? I'll come with the solutions. I will discuss it because some of you may have it difficult to grab the solution. So let me complete the note. Another 2-3 weeks, I'm going to complete the lecture note in the maximum of 3 weeks time. So once the note is completed, then I'll go over the tutorial. I'll use the lecture time to go over the tutorial with you. I will voice over it and I'll also upload it online for you so that you can go there and read as many times as possible. So as per the test, one of you sent an email to me asking about the test for July. I don't have. I want the school to come with the calendar first, the plan. I don't want it to prepare for tests and the school says the test is not going to be used. It's just a waste of time. So let's just wait for a week or days and let the school come with the plan. Once we school have the plan, then I can also always put my test or my assessment to go along with the plan. So let's hope between now and next week we get a plan from school. Then from that plan, we're going to know what to do. Definitely our test one we can't. The test we did before the lockdown, we definitely can't. You know, we had test one before the lockdown. Definitely that's I know it we can't. But let's forget about the other tests. Let's hold on for now. And let's see what the school is saying before we know what next to do. So this is the lecture for this week. I'm going to put the tutorial on Moodle in the next 20-30 minutes. I'll put the tutorial for this week. Try to work on your own. And at the end of the week, I will see how far I can go with putting the solution online for you. Okay, any comment or any question for me? Any question or any question? Oh, somebody is saying, is there an assessment on Wednesday? Do you want assessment this Wednesday? July 1. Let me throw the question back to you. Do you want assessment on Wednesday?
No, sir.
Why no, sir? Why no, yes, sir? Why no, sir? Okay, there will be assessment on Wednesday. The referee is saying there will be assessment. Then you must go and study. Okay, let's leave it for now. Let's see what happened this week. I think by next week we should have a tentative day for our assessment. Let's forget about Wednesday this week. So there will not be assessment on Wednesday. Okay, let's agree on that. Let's hope that before next week we'll get a date. I won't give you assessment without telling you the date. I'll give you 1 or 2 or 3 days to prepare. So let's plan that this week no assessment. If I'm going to give you assessment, I'll give you a notice that there will be assessment and I'll tell you the date and the time. Okay, thank you very much. Enjoy the rest of the week. Okay, you can still connect tomorrow for your tutorial. Let's see whether we have 1 or 2 things to say. So tomorrow we have tutorial. We'll not spend for 45 minutes. We can just chat and discuss. For a few minutes, then you start working on your own.